give it a check, see if it'll. Yep. All right,
Hey.
perfect.
Where's the timer?
Time is there.
And I've got cue cards
Yep.
for.
There's a
That's not
microphone
good
right
enough.
here as well. Yeah, who's speaking first? All right, welcome back. So our next talk is P-sampling Kubernetes network policies. And this will be Nadia, Dumitru, and Adrian.
All right. So we'll talk about Kubernetes today a little bit. I'm Nadia. These are my friends, Adrian and Dumitru. You already know them. To understand the problem, we'll have to start from the beginning. So Kubernetes is a container orchestration engine, just in case someone doesn't know. So what it does is it groups containers that make up some application into a thing called pod. And you need to know that to understand the demo. Different cluster resources in Kubernetes, including pods, are isolated using namespaces. These are not Linux namespaces, these are Kubernetes namespaces. Pay attention to that. And there is also this concept of labels in Kubernetes, which is just key value pairs that are attached to different objects, including namespaces and pods. And labels are supposed to help you select different objects in your cluster. So on this example, you can see there are two namespaces. One is default, another one is my project namespace. They have two pods, and one of the namespaces has a label with this project name. Now, network policy is a Kubernetes API that ensures network security. What it does is just allows and denies connections between different pods. Here you can see an example YAML. That is how you configure network policies in Kubernetes. What it does, it selects pods that are isolated. So what you can see here, it's like all the pods in the default namespace, basically pod A, will be isolated. And the only connection that it allows is that pod B. And what it does is it uses namespace label selector to choose from which pods we want to allow connections. And they can go in ingress and egress direction. So in this network policy, you can see it says ingress. Now, what is the problem with that is the observability. So in real clusters, the amount of network policies can reach thousands and thousands of network policies in different namespaces. So at some point, a connection may be allowed or denied, and it's pretty hard to figure out which exact network policy does that and why it happens like that. So here's an example. You may create multiple namespaces. And let's say you wanted to allow all connections from namespace 1. And at the time, there was just one pod, pod B. So you selected the pod. But then you create another pod, which is pod C, and you want to allow connection from it too. And you thought, oh, I wanted to allow full namespace, but in reality, you just allowed one pod, so the connection is denied now, and go figure out which network policy is configured wrong. Okay, so OVN Kubernetes is a plugin that implements Kubernetes networking using OVN. That part you know. So to implement network policies, OVN Kubernetes uses OVN ACLs. And that is kind of how it looks like. So you have a network policy that is translated into ACL. And then at some point, a packet comes, it matches an ACL. I would really like to have some observability agent so that it could see which packet matched which ACL. That's not there by default, I should tell you. And then basically what this observability agent could do is just knowing which ACL a packet matched, I could just read some external IDs and figure out which network policy created this ACL. So then I could tell to my user, okay, this connection is allowed because of network policy A in namespace B, which would really help them figure out where exactly the problem is. So that sounds really nice, but how do we do that? And that's where you need some friends to help you.
Yeah, thank you. So, yeah, like Nadia said, network policies are implemented with ACLs, but how do those actually look in OVN? Of course, it's not simple. Well, actually it is, but it looks complicated, but it's not. So you normally have a default deny ACL, that's the red one there at the bottom. And then you have allow rules to open up holes in your firewall. Here we have two OpenShift nodes, two Kubernetes nodes. Each of them has an OVN topology, with OVN switches, the pods are connected to the switches, and ACLs are applied to the pods according to the network policy definition. I'm not going to insist too much on this. It's more just to show the important stages in the OVN pipeline when packets hit ACLs. So first, we have a look at the contract to see if we already knew that session. Here we're looking at the TCP SYN packet, so a packet that creates a TCP connection. Because it's the first packet, we don't have a contract entry. So what we're going to do is match on the explicit ACL that actually allows this packet, because that's what network policy said. Next steps, we're going to commit that entry to contract. And then the reply comes. And we do kind of the same thing, but in the other side of the pipeline, so in the egress pipeline of the switch. We're going to do a contract lookup in the pod's contract zone. We're going to find the entry there. It's going to set the flags to track the established reply. And then we have an implicit allow rule, because our ACLs are stateful, that are going to let the packet pass through. That's what happens here. Right, so what I showed now were plain ACLs. We still have no visibility. And it turns out that OVN actually has or had features before 2409 to provide some visibility into ACLs. 2 of them actually, ACL logging and ACL labeling. So you might ask, yeah, why not use those? So I'll just quickly show what those features do. First, the logging one. Here on the top right, here on the top right, I show how you configure it. You basically attach a label, just a number, to the ACL, a name, and enable logging for it. And what that does is every time the ACL is hit in the data path, it's going to generate an up call to obvious vSwitch, which is going to generate a packet in the OVN controller where it gets syslogged. As you can imagine, that's not nice. It's super slow. So we can't really use this. And then we have a related feature. It's called ACL labeling. It doesn't really give you insights about what ACLs were hit for every packet. But what it does is attaches a label to the ACL, and then whenever we commit that session to contract, we store that label in the contract entry. So then later, if you have a side application or whatever that monitors contract events, you could kind of figure out what ACLs were hit. But you still don't really get information per packet. So that's why we ended up writing a new feature. It kind of combines the two. And the nice part is we could actually reuse most of the OVN pipeline for this. And what we do is we added some new tables to the northbound database. You can configure sampling collectors. Oh yeah, maybe I should start with the fact that OVS supported IPFix for a long time already. And IPFix allows generating samples from the data path to IPFix collectors. It has some issues because those samples still need to go to obvious vSwitch, and then vSwitch will eventually forward them to the IPFix sync. But yeah, from OVN perspective, this is kind of an implementation detail that doesn't really matter to us. It's a data path specific thing. So what we actually ended up doing was empowering OVN to use IPFix sampling or sampling in general. So you can today in OVN 2409 define a sample configuration where you attach some metadata to the sample. That's kind of like the label ID that we had with ACL labeling. And you can attach 2 different types of samples to ACL. A sample configuration for new traffic, so traffic that creates new connections, and a sample configuration for established traffic, in case you want to sample those at different rates. Maybe you don't want to see all the traffic. Maybe you want to see only the traffic that creates connections. So yeah, the ACLs change a bit in the sense that we attach these sample configs, but that's about it. And then what you get in the data path is your action will, well, this is with IPFix, but with psample it's very similar. You're going to get some sampling actions being generated in the data path that actually embed the labels that we have in our configuration. So your sample receiver, your IPFix sync, or whatever we're going to see connected to the P sample here that Adrian is going to talk about, will get the metadata that was actually configured in the northbound database by OVN Kubernetes. So it gives us a way to trace back to the network policy. Yeah, how that happens, it's basically the same sequence of events as before. I just highlighted the differences here. So what's different is that we have this new sampling config. And then we do the same thing for the SYN packet. We do a lookup. We don't find the entry. We have an explicit ACL that matches the packet. So we're going to tell it to commit to contract. But we're also going to store these two special values here, the ones that are in the sampling config, in some registers. And later when we actually commit, well, in this case, we're committing, but we're also generating the sample because it's the first packet. But what happens is, at this point, our state, oh, I forgot to put it here. But yeah, we commit to contract, but we actually store in the label the value from the register. So the sample, the observation point ID, we call it, but it's just the value that we attach to the established sampling rate, sampling configuration. So this is going to be stored in contract. And then when the reply comes, again, we do a lookup in the same contract zone, but this time we find the entry, tracked established reply, but with the observation point ID set. These are 32 bits, by the way, so it probably works with offload. Yeah. Sampling, not really, but yes. So what happens then is we're going to generate actions for the reply traffic, even though we didn't have an ACL that explicitly matched reply traffic, it implicitly matched it. We're still going to generate samples for it, which are going to point back to the network policy that created the ACLs. That's just for completeness. Okay, so what's good about this? We get per packet ACL information. We can distinguish between packets that create new connections and packets that are part of existing connections, established connections. It's data path agnostic. It works with IPFix, and it also works with psample. That's supported by OVS 3.4. The not so good is we had to add additional flows for the reply traffic to explicitly match on the label value because, well, because we had to, and that creates a control plane cost. But then Adrian had a really great idea, and he said, wait, can't we generate samples that take the value, the metadata that we embed in the sample from a generic field, OVS packet field. And that packet field can actually be the city label. So that's what we ended up doing. When, if we run with OVS 3.4, we can actually generate, instead of a flow per ACL, we just need two generic flows that load the observation point ID, this one, into the sample action directly. So this is a logical flow here, but it's very similar to the open flow that gets generated. And we have two of them because reply and not reply, we could probably merge them, but it's not a big deal. So that's how it looks at OVN level. I'll let Adrian speak about this.
Okay. So from the OVS, so we go one abstraction layer below. And from OVS perspective, this is what we had before. So this is the existing IPFix infrastructure per flow sampling infrastructure. I'll not get into much details, just we have an open flow that specifies observation point and observation domain IDs. This is the metadata coming from OVN. How it worked is we translated this sample action into a data path action that is basically sample with some probability and user space. So an app call. We send the packet with the metadata. We send the packet from the kernel up to user space. We create a cache, build the IPFix frames or whatever, and eventually at a certain point, we send them out through a UDP socket. So of course, the main problems are the upcall. Each packet that gets sampled will be upcalled. It's sent to OVS vSwitch D, which is overloaded. But more importantly, it shares the same netlink socket as actual upcalls, like flow misses, which means that we could very easily get packet drops. And there are all additional problems like contention, thread contention, and so on. So our goal was to come up with a solution that would basically bypass OVS vSwitch D altogether. So, and have these metadata alongside the data, alongside the packet. So we looked at the kernel infrastructure and we found this psample module. Psample exists for a long time. It is used by TC. It's great. Creates a netlink multicast socket, multicast group, and you can attach to it. It has a group ID, which kind of selects the source of the sample. So it kind of matched. It didn't have metadata with it, and it was kind of suboptimal because a packet copied was created even if there were no listeners. So we added user-defined metadata, and we optimized that. So now we have a kernel infrastructure that we can use from OVS. So we created this data path data path action called psample. We added a group and a cookie that is essentially whatever OVN gave us. It integrates with other data path actions such as trunk or sample, which does the rolling of dices and probability calculation. And so the only problem, so once we had that, we just had to receive the sample action and translate these observation point and observation domain IDs into our psample action, and that's it. The problem is, as Dumitru said, that what we were receiving is a bunch of these actions. So each action would, each flow would match on a specific label and add that label into the observation point ID. Match on a label and add that label. So we had to basically optimize that in OVS by improving the existing OpenFlow sample action to be able to express this. Now the sample, the observation point ID of the sample can be extracted from whatever OpenFlow field, such as the contract label. And those were pretty much the optimizations that we had to do. And for completeness, this is how the new flow works. The sample action is translated into a sample with a probability and a psample action. The kernel data path sees the packet, sends it to psample, and the psample just sends it out on a netlink socket. Netlink multicast group. Now, if you wanted to use some very fashionable technologies like such an eBPF, you could probably also just hook into whatever psample, func kprobe or whatever, find a place and just extract the data from there if you don't want to speak netlink for whatever reason. Future work on this area. We want to publish performance tests that we are currently running, right? We will on a Red Hat blog, hopefully soon. And there's an area to explore here, which is, of course, this psample stuff is only implemented for the kernel data path. We would like to listen to use cases for this kind of sampling in the user space data path and come up with a way of implementing the same in the user space data path. We could use USDT probes maybe, but yeah, there's lots to explore there. So yeah, future work. And now, let's look at the demo.
I don't think we have the time to look at the demo. Okay, it was supposed to be for question. Okay, yeah. Anyway, so there are multiple ways to consume the samples, as Adrian said. One of the ways, which is easy to understand, so that's what we're going to show in the demo, is some graphical interface, and that's what you can see here from the OpenShift Net Observability Operator. That's basically how it looks like. So you can see there are multiple flows that exist in the cluster. It shows the source and the destination. It speaks in terms of pod names, even though they have IPs in real life, but it's easier for Kubernetes users to understand it like that. And you can see the new field, network events here, which is exactly the sample that's being sent. Okay, let's try to run this one. Okay, so that's a Kubernetes cluster running locally. There is this application, which is really simple. It's an iPerf server running on port 5201. What happened there? And a client that connects to that port. This application is not running right now, but we'll run it just in a couple of minutes. Okay, so there are a couple of network policies in this namespace, the egress and the ingress wrong port, which should give you a hint, but usually you don't know it's wrong port. So egress 1 allows egress traffic from the client on the right port, and the ingress 1 allows traffic coming from the client on the wrong port, but supposedly you don't know you've specified the wrong port. So what we do is we just run this application. So the server is being started right now. We are giving it a little bit of time, and the client tries to connect to the server, and nothing happens because the connection is denied. That's not potentially what you expect. So then you go to this interface and you refresh it and you try to see which flows you have. So there is source client, destination, server port. It shows the port on which it's running, 5201, as we wanted. And in the list of network events, you see egress is allowed and ingress is dropped by network policies. So basically at this point, you're like, why is it dropped? I added an ingress policy that allows it. So you go check your YAML and see that the port is wrong. So you're like, oh, I should edit that. You go fix the port number, fix the error, run the application again. You should guess what happens now. It runs from scratch, so we need to give it some time to start up. And now the client will initiate the connection, and hopefully it will work. It's a pre-recorded demo, so it should work. Okay, connected, everything worked. We go to this interface again, just take a look at what's happening. It's sorted by the timestamp, so you can see the latest connections on the top. And what it says now is that it's allowed in ingress and it is allowed in egress directions, which is what you expect. So basically what it helped you do is figure out when the connection didn't work, which exact network policy dropped it. So we had just 2 network policies, so it probably looked easy, but if you had thousands of network policies, that would be difficult. And this is we won't spend too much time here, but these are basically just 2 ways that we implement right now of how you can collect samples. So this net observability side is what we've just seen in the demo in this nice interface, but there is also another way which is actually connects to this netlink multicast group and just dumps everything into the terminal, which is less pretty, but you can still do that. Okay, and that's it. Any questions?
Okay, we do have time for questions, and yep, looks like we have one.
Thanks a lot. Are there any version requirements for the kernel to get these new fancy features?
Yeah.
Yeah.
It's 6.11. Yeah, 6.11.
Yeah. Actually, on that note, Adrian did a lot of work for the OVS self-tests in kernel. So I just want to call out that for him. They actually now run for every single patch that's submitted to the kernel net tree. So we get Open vSwitch self-test running and reported. So yeah, thanks. Including psample. Yes. Okay. Do we have any more questions? Oh, yeah.
Thank you. You have a probability of packet capturing. Is it so? It is possible to not catch the drop, right? And is it possible somehow to make this probability higher to catch
You can set probability 100%, and you catch everything
for drops?
for everything, for every ACL, every type of ACL, and
Okay,
also for default drops. It works in the same way.
good. Thank you.
Okay, did we have any other questions? Any from online? Okay, let's thank our speakers.